We're going to talk about the velocity structure of molecular gas in FRB.
Good afternoon, everyone. I'm Tzu Yin Hsu from National Tsinghua University, and I'm a third grade student. And now I'm working with Professor Hashimoto, which is a previous talk. And before the talk starts, I want to acknowledge the UCAS Summer Student Program to support me for this summer project. And today I'm going to introduce my talk, the velocity structure of molecular gas in a non-repeating FRB, 180924b. And this is my outline today. I will introduce what is fast radio burst first, and I will go into my project, starting with results, discussion, and end with conclusion. So what are fast radio bursts, or FRB in brief? Fast radio bursts are millisecond duration radio transitions with this brightness to jump speed level, and they are generally come from cosmological distance. So far, there are about 800 FRBs that have been detected, and they are all classified into two types. One is non-repeating FRB, or we call them once-off events. Another is repeating FRBs, or we call them repeaters. Actually, there are more than 1,000 FRBs on the sky every day. However, we have never known its origin. To understand the origin or the progenitor of the fast radio burst, we would like to constrain its physical environments of its host galaxies. In the previous optical observations, most of the research is focusing on its stellar components, and both non-repeating and repeating FRBs shows diverse properties in their host galaxies. We have known very little about the gas condition, which will trigger the star formation that is likely to result in FRB activities. Therefore, in my research, we will provide the first analysis of the molecular gas kinetics in the FRB host to understand the progenitor of fast radio bursts with ARMA telescope in sub-millimeter wavelengths. And this is our target today, the host galaxy of non-repeating FRB 180924b. It is a massive early-type spiral galaxy with a redshift of 0.3216. To investigate the molecular gas kinetics in the host galaxy, we would like to detect the CO emission line. And this is a velocity integrated intensity map with the integration range from negative 180 km per second to 110 km per second. So we can see that in the large red circle there is which is the host galaxy region. There is a very clear CO emission detection, and this is also the first CO detection in the FRB host. And this is the CO spectrum in the host galaxy region, and the blue line is the observed data, and the black line is the Best-Fit Gaussian function, and the orange line is the CO emission line. And we can see that the center of the second component is aligned with the CO emission line, which also indicates the CO emission detection. And in this spectrum also shows a asymmetric profile, which may indicate the disturbed kinetic structure of molecular gas. So to test if the spectrum is really asymmetric, we will apply an asymmetry parameter, A peak. A peak is the peak ratio of the two velocity components. So the higher the A peak is, the more asymmetric the spectrum is. And we also compare our results with two FRB hosts, which is regarded as asymmetric in their H1 spectrum, and two gamma ray burst hosts, which is regarded as not asymmetric in their H1 spectrum. So we can see that the A peak value of our target is very high, even higher than the two asymmetric H1 spectrum of the two FRB hosts. And this indicates the CO spectrum of our target is very asymmetric, and also indicate the disturbed kinetic structure of the molecular gas in the FRB host. And we also plot the velocity structure of the host galaxy. And we can see that in this figure, the velocity structure shows a smooth velocity gradient range from negative 180 km per second to 8 km per second. And there is no positive velocity component, which shows a symmetric velocity profile. And this also indicates the disturbed kinetic structure of molecular gas in the host galaxy. And thus, we overplot the CO component in the velocity integrated intensity map in grayscale. So in this plot, we can see that there are multiple spectral components in this plot. And with the asymmetric CO spectrum and the asymmetric velocity gradient and the multiple spectral distributions in this map, we conclude that there is a disturbed kinetic structure of molecular gas in the host galaxy of non-repeating FRB 180924b. And we also compare our results with the H1 detection of 3 repeating FRB hosts. And this is the 3 repeating FRB hosts. And for the first one, the host galaxy of FRB 180916b, the velocity structure shows the 2 velocity components, which one is positive and one is negative. And there is a halo between these 2 components. And this shows the merging H1 gas and also indicates the disturbed kinetic structure of H1 gas. And for the right panel, there are 2 H1 spectrums of 2 FRB hosts, FRB 181038 and FRB 200130E. And these 2 host H1 spectrum all shows asymmetry, which also indicates the disturbed kinetic structure of H1 gas. Okay, and in conclusion, we provide the first analysis of the FRB molecular gas kinetic structure of FRB host, and we conclude that the host galaxy of FRB 180924b, which is a non-repeating FRB, shows a disturbed kinetic structure of molecular gas. And also, we found similar H1 kinetic structure in the repeating FRBs. And thus, we conclude that there is a disturbed kinetic structure in both non-repeating and repeating FRB. And this may suggest a possible progenitor between the gas kinetics and FRB progenitors. Okay, thank you.
Question. Any question from the audience? Yes.
Hi, thank you for the interesting talk. Well, I would like to ask, could you provide any specific link between the FRBs, the happening of FRB and the environment? I mean, they are all from a specific galaxy, and we know that there is a CO environment, and we know there's FRB coming from it. But can we have any understanding between the link of these CO environments and FRB? Or just because the FRB comes from a galaxy with CO environments?
Oh, okay. So the CO emission line can have a conversion with the CO luminosity can have a conversion with the molecular gas mass. And the molecular gas is the source of star forming. So if we know the gas is like rotation or disturbed, and this may link to if this host galaxy is star forming galaxy or not star forming galaxy, or crescent galaxy, something like this. So that's the reason why we detect the CO emission line. Thank you.
Okay. Any other question?
Oh, I see. So, actually, we use the AMA telescope to detect the CO emission line, and there are 6. Because we want to, at first, we want to put a constraint on CO luminosity, but there are only 6 CO emission, CO detection in the. Oh no, there are only CO observations in the FRB host, and this is the only one has the CO detection. That's the reason why we choose this as our target. So this is the first CO detection too.
Okay, any other question? Yep.
for the interesting result. Just curious whether for this particular source you have the H1 observations too, because you have H1 observations for the others.
Sorry, can you?
So whether you have H1 observations for this particular galaxy?
You mean the target?
Yeah.
Oh, we don't have the H1 observation for this galaxy.
Thanks.
Thank you.
So we are planning to do that, actually. Thank you very much.
So, any question? Well, actually, I have a question. Notice that you are talking about CR and H1 symmetry, so you say it could be due to the gas property or
Yes.
something. But in your supervisor, he said that most of them are old population. So,
Yes.
so would you comment on your supervisor? Do you want?
Yes, that's the problem. So, okay, so for like the host galaxy of 200120E, its host galaxy is NTHU, and it is in a global cluster, which is an old population, right? And but this FRB is regarded as in the star-forming galaxies, because it have interaction with NTHU. So the old population doesn't mean that it doesn't have star formation, I think.
Okay, I think we need to move on to the next speaker. So thank you.